I'm Neven Miculinić. First, I will briefly introduce myself. I started programming when I was about 12 with some algorithms and data structure competitions. From there, I did my university degree, during which time I was an intern at Facebook. And over the last few years, I did various projects, from developing cryptocurrency trading bot to developing DNA deep learning base caller and various DevOps projects. Nowadays, I'm a DevOps and a system engineer at Luci. At my previous company, I was doing Internet of Things development with Kubernetes. We were using, okay, laser is not working. We were using BeagleBones for deploying Internet of Things workloads on edge devices. And during my experimentation with it, I encountered some issues, notably performance issues. So stock Kubernetes, without any special tuning, consumed almost 30% of CPU usage on such hardware, which is only kubelet and node agents, of which the kubelet consumed about 20% of CPU usage. Therefore, this gave motivation for this talk to actually dig down and understand what a kubelet is doing. Because before this happened, I had an idea in my head that kubelet is like a simple node agent which does basically nothing, which is far from true. So, this is like the basic Kubernetes architecture, just to remind ourselves. We have the control plane, which calls the etcd, kube APS server, and kube controller manager, etc. And we have Kubernetes node, which hosts kube-proxy, kubelet, and pods. Pods are our actual workload. If we read documentation, they say the kubelet is the primary node agent that runs on each node. The kubelet works in terms of pod spec. Therefore, for the rest of this talk, I'm going to go with kubelet from the perspective of the pod. So we start with the pod journey. First, it's created on the API server by either some controller like replica set or daemon set, or we create it manually. It runs through various validation hooks, admission hooks, mutating whatever. And finally, it's scheduled on the node. Kubelet periodically syncs with API server to check if there are new pods I should be running. If so, the pod lifecycle begins. Every pod starts in some kind of pending state. Before the pod even starts executing on the node, a bunch of pod sync handlers are executed. If any of those fail, the pod reaches failed state. It's either restarted, rescheduled, or some other operation depending on configuration. Pod enters a running state. If everything goes fine, it will succeed. If not, it will fail. And there is one final state called unknown state. This is when you have Heisenberg pod. You have no idea whether your pod is alive or dead, or something funny is going on, and you need to probably intervene manually. So this is the communication between kubelet and API server. It uses typical public key infrastructure, which all controllers use with Kubernetes API server. The kubelet in particular has a common name, system node name, and organization system nodes. And it periodically updates the API server with its pod status and its node status. There's also communication in the other direction. For some reason, for example, you do kubectl get logs or kubectl port forwarding, whatever. This communication goes from your kubectl process to API server and back to kubelet. For this, there is a special public key infrastructure which has a certificate authority of the kubelets, and API server has its own private key and signed certificate. So the pod has been scheduled on kubelet, and we are ready to start it. First, those are those pod sync handlers I mentioned earlier. And the first ones are various admission controllers, like checking if the app armor profiles are properly formatted, if the no new privileges is obeyed as a Linux flag, and some other stuff. Then data directories are created. Those are used for pod logs, for mounting the volumes, and some other use cases. The volume manager syncs the spec volumes within those previously created folders. So it fetches the secrets if they are mounted as a volume. It fetches the configuration maps if they are mounted as a volume. It somehow mends the persistent volumes depending on the type of the persistent volume, etc. And also all the secrets defined for image pool secrets are pulled and are prepared to fetch the images the kubelet will run. If you look at this file called kube-runtimemanager.go, you will find this comment. It's literally copy-paste ad verbatim. So what's like the kubelet synchronization algorithm for running the pods? First, I compute the sandbox and container changes. Kill pod sandbox if necessary. Kill any containers that should not be running. Create sandbox if necessary. Create init containers. And finally, the normal containers. For all this description, there is some mysterious term. What is the pod sandbox? So because kubelet is written so generically, it doesn't really care that much what its runtime. The sandbox is some kind of abstract concept of isolated entity. If you're talking about Linux namespaces, it could be basic isolation of all the 7 Linux namespaces. And this is some kind of sandbox, some isolated environment. If you're using something like virtual machines, we basically have a virtual machine isolation with virtualized CPU, I/O operations, and a memory. Either way, the kubelet can use it. And it uses some layers of abstraction. So you have a CRI, which is Container Runtime Interface, specifically designed to make kubelet more runtime agnostic. So you can easily switch between runtimes, whether it's ContainerD, Docker, Creo, Rocket, or whatever else you want. Those container runtimes are responsible for various pod managements in the side of the lifecycle and for pulling and garbage collecting the images. After a container runtime does its job, it prepares a root file system for the container and bunch of configuration is JSON manifests and hands this over to the actual runtime like runc, gvisor, or keta, who start the pod and do all the necessary jobs. Container runtime interface is defined as gRPC remote procedure call service. Here is a abridged copy-paste of the spec you can find on GitHub. There is a service, image service, which does CRUD operation on image. So this X is basically read, create, read, update, delete. So typical CRUD operations. There is create, read, update, delete the pod sandbox, this isolated environment. Create, read, update, delete container. And there is execution within the container, attached to a container, port forwarding, and fetching container stats. One thing that is missing here is kube catalogs. Because kube catalogs work a bit differently. When you configure the pod sandbox config, you also gave it where is the log directory where I save all the log data from the containers. The more that you look at CRI specification, this is configuration, the more it looks like typical pod spec from the Kubernetes. So you can see here we have the host name, the DNS configuration, port mappings, labels, annotation, etc. If you talk about typical runtime, which does Linux namespace isolation, usually the first container which is run in this isolation is called the post container. It's responsible for setting up and holding all the Linux namespaces. And because it's the first one in its PID namespace, that is process namespace, it has PID of 1. Because of it has PID of 1, which is a special process, which is an init process, and it's responsible for reaping all the zombie processes within your pod. Now, we're going to talk a bit more about how does kubelet and CRI do resource management, and they are using a tool called cgroups version 1. Today, there exists cgroups version 2, but for some technical reasons, most runtimes actually use version 1. It includes a bunch of controllers mounted at special path in the file system. So sys, fs, cgroup, and then the name of the controller. So CPU controller, memory controller, CPU set controller, and then there are like 5 more. And under this path, for CPU group sys fs c group CPU act kubepods, will be all pods located which are run via kubelet. There is a special flag with kubelet called cgroups per quality of service. If this is true, you will have another folder per each quality of service. So one folder for best effort, for burstable, and the guaranteed quality of service is in root cgroup, so this kubepods. Ncube and container runtime basically configures the parameters for CPU and memory to enforce the CPU requests and limits and memory limits. For the CPU, for the request parts, this CPU share is important. And if you enable the CFS quota by kubelet, the kubelet will also enforce the CPU limits by using CFS period microseconds and limit microseconds. For the memory is limited only, so the limit is enforced, while the memory requests are only used during scheduling as a hint to kubelet how much can you overcommit each node. As you can see, from the CRI gRPC spec, there is Linux container resource, basically accepting all these parameters. So CPU quota for memory stuff, out of memory score adjustment, and there is one additional field called CPU sets CPU. Those are most commonly not used except in one scenario. If you have a container which is guaranteed quality of service for the CPU, so it has the same amount of requested CPU with the number of limited CPUs, and those are the integer number, your container gets dedicated CPU cores, that is, your process is CPU pinned to those cores and forbidden from using it by other pods and containers. This has additional benefit of better cache hits and less context switching between threads from different cores. So what about networking? Because, as I mentioned again, Kubelet is written pretty generically. The networking also has a plugin-based model called Container Network Interface. In this model, plugins are used for managing network namespaces. That is, for managing network interfaces within those namespaces. Specification is a simple JSON file, usually located at Cni net.d. And all the binaries which actually run the plugins and set up the interfaces are usually in opt Cni bin. If you look at the common network plugins like Flannel, Calico, or vworks, you would see their pods. What they do, they actually mount the host path of those two for configuration and for the binaries, and copy their config within the etc Cni net.d, and copy their binaries within opt Cni bin. So how does this configuration even looks like? This is the most simplest example. If you have a proper binaries and you run Cni with this information, just do this, it will create a loopback interface within your container network namespace. This is more complicated example. It does quite a bit more. It creates a virtual bridge within in the root namespace, and all the containers will have a virtual add pair between the container network namespace and the root network namespace, and every of those interfaces will be connected into virtual bridge. By using isGateway is true, we are going to set up the routes for the containers to actually route everything outside of the host through this gateway interface, using this bridge as a gateway interface. By using the masquerading with IP masquerade, each pod communicating with outside world will get its IP'd net and masqueraded. And the last part of the puzzle is something called APEM, IP Address Management, which allocates IP addresses to each container. We can easily set it up, but using something called IPEM is host local within this subnet. So if you want to, you have some fixed number of nodes, and you want to handle the routing manually without any CNI plugins like Flannel, Calico, or whatever you want to use, this is the most simplest approach. You just assign some seeder per each node, set up the routing tables in the root namespace, and just use the host, the bridge CNI configuration. For something more serious, this is the typical funnel configuration, which funnel installs for you automatically by using its daemon set. It consists of two plugins, Flannel and Portman. Flannel sets up the interface for communication, and Portman is one plugin which is commonly chained within CNI. Its main responsibilities is for handling host port configuration within pod. So if your pod requires some host port being forwarded to it, you usually have to use Portman, or otherwise you wouldn't have this capability. So even if in previous case, if you require this, you would chain the bridge plugin with the Portman plugin. And here is Flannel specific configuration and Portman specific configuration. The type usually means the name of the binary within the binary folder. Now comes the question, how do we even run all this CNI stuff? So we have the plugin name that is type. This is the name of the binary. We pipe the configuration via the standard input, and we pass extra configuration by using environment variables. So if you want to try it out yourself, you create a new network namespace. You go into it, or you don't have to, doesn't matter. You just need a path to this network namespace. So it's CNI network namespace. And you can execute your network plugin and see what it will do. You can go into this network namespace by using nsenter, which is really useful utility if you have to do some debugging on the node. The first command, nsenter --net equals to network namespace, enters this network namespace and usually executes bash or something like that. If you want to enter more network namespaces, like the second command, you can enter network namespace, UTS namespace, mount namespace, IPC namespace, PID namespace with -t equals to target process. If you have some runaway container doing weird stuff, usually in a container, you don't have TCP dump because most container images don't hold TCP dump. What usually I do is simply enter the network namespace of this container and run TCP dump because the mount namespace is my root mount namespace, and I have TCP dump installed on my nodes. So finally, I'll talk briefly about kube-proxy. This isn't directly related to kubelet, but it's just one other component running on every node, which handles the translation between cluster IPs to pod IPs and some other minor responsibilities. There are three modes of operation for kube-proxy. One of these is user space proxy, which is slow, and it's probably nobody uses it anymore in production. There is Iptables mode and IPv6. Iptables mode works kind of like this. You have outgoing chain, where each service IP is matched. So you go to service 1, is my destination IP equals to service 1 IP? Yes, no. Is my destination IP equal to service 2 IP? Yes, no. Yes, no. And if it's so, you jump to another chain. There is a chain per service. And this chain per service is probabilistic. So basically go by probability of 33%, I will jump to pod 1. Otherwise, I execute the next rule. By 50% probability, I will jump to pod 2. Otherwise, execute the next rule. This works okay if you have something like 10, 20, 500 services. However, if you have a large number of services with large number of pods behind them, this becomes quite slow. So for the most biggest clusters, what's usually used is called something IPVS. For this, we have a hash map within the Linux kernel, which maps the service cluster IPs or virtual IPs, however you want to call them, to various pod IPs backend. With kube-proxy, you can actually choose what will be the load balancing algorithm for IPVS. By default, it's round robin, but you can choose some other load balancing method if it suits your use case. And finally, Kubelet does a bunch of stuff in a looping manner. So a bunch of reconciliations. We talked a bit about volume manager. It's also responsible if the secret of config or config changes during the pod lifetime, and those are mounted as volumes, it will refresh them. It's also responsible for emitting health checks and checking the health of your pods. It's responsible for pod lifecycle and event generator. It's responsible for container garbage collection, for exposing runtime statistics. Its responsibility is also image management, so that all images don't overflow the hard disk memory of your nodes. For fetching node statuses and updating to the API server, for certificate rotation within the API server, and expose a bunch of Prometheus metrics, which is quite a lot. So to come back to the original example, where on my BeagleBone, which is really weak piece of hardware, finding that bare-board Kubernetes without any workloads uses 30% of CPUs wasn't that much surprising. However, Kubelet also exposes Go's debug ports and debug endpoints. So the usual things I did was fetch the Go's tracing and go on pprof profile and analyze them. I also ran perf on my nodes to see what it's doing from the kernel side. After all this, I discovered that for Kubernetes version 1.13, about 25% of the time was spent in various housekeeping sync loops. For my particular use case at this job, I didn't really care about these housekeeping tasks, so I effectively disabled them by setting the housekeeping interval to 10 minutes. Also, the Docker shim, which is default in stock Kubernetes installation, it's quite resource heavy compared to ContainerD. Therefore, I replaced it with Cni ContainerD. Another interesting fact, which I have no control to change, this was ARMA version 7 process, Cortex something something. And its CPU has really bad branch prediction algorithm, which basically has a branch miss rate of 30%. For comparison, for your common case Intel x86 architecture on your servers or laptops, you would see this something like 0.5%, 1%, maybe 2%. So this is quite horrible. Basically, your kubelet or any process running on this node is trashing the CPU pipeline all the time. So it's no wonder it's slow and not performant. After all these improvements, I managed to cut down the CPU usage to 15%, which was good enough for this use case. And with this, I'd like to finish my presentation and open for questions. If somebody is interested, this QR code leads you to presentation slides.
What is the housekeeping work usually Kubelet is doing, which you have increased the time to 10 minutes from 10 seconds? What is the impact if we don't?
So one of the biggest time sinks was measuring statistics. So runtime statistics, like how many CPU and memory the pod is using. This version actually used cAdvisor, which was embedded within the kubelet for version 1.13 of Kubernetes. Modern kubelet actually moves to using CRI. So the CRI is responsible for replying with metrics from the pods. So it's maybe a bit bitter architecture, but for my use case, I don't really care how much resource something is using. I want it only running and health checked. That's it.
There's no functional impact of increasing this time?
Depend what you want.
Just like scheduling pods and if not interested in stats, but functionality, it will work for the life cycle of the pod?
I'm not 100% sure, because I don't really care about scheduling pods every 10 seconds. But it will check for restarts and everything, so we should check the details.
The branch prediction, can you optimize this? Can you compile it for a different variant of the ARM board? Is it how you could change it, or how can you improve on the branch prediction part?
I mean, technically, that's a compiler job. But Kubelet uses typical Go compiler, which is only a single implementation. It's single backend. So I'm not sure can you really do much with it. Maybe with LLVM or some more advanced compilers, maybe, probably, there are some flags which are better suited for embedded development, which usually have really cheap CPUs, which have poor branch prediction algorithm. I looked at the other processes in this machine, so systemd process or natively compiled RMHF C++ programs. They all suffer from the same problem, and they were actually compiled specifically optimized for this platform. So I guess at the end of the day, most of our code we actually write for some business use case or infrastructure is a bunch of pointer chasing, and you have a bunch of branching and stuff.
Okay, thanks.
Does anybody else have a question? Okay. Thank you for watching and your attention.